the end of the Second World War, there were already these kind of machines that were used for the teletype encryption machine. They were used for the encryption. It was, of course, very important for the military, and it turns out that the electromagnetic radiation, the emanation of this device, could be seen from another building, from the other side of the street, from an opposite building, and one could see the plain text that is encrypted with this machine. So that was, it's already known a long, long time that there exist side channels. This was, then the Tempest project was founded by the US government that investigated how to protect cryptographic devices that they do not leak so much information. You might also have heard that it's very old, that it's possible to see the content of the video screen of them old monitors or TVs that use a beam to produce the pictures before the invention of the TFT or LCD displays. And you could also see the password that is typed in on the screen then from another room, for example, only from the radiation of this beam that draws a picture on the screen. Yeah, so it was only that the secret services and only the intelligence community knew about them. Side channel attacks, a very poor understanding for normal people, until the second half of the 1990s, when the golden years of side channel attacks started. So, for example, there was a fault attack on RSA, fault attack that you shoot at the cryptographic device with a laser or with a flash to produce an error and in the output. And if you've got this output with the error, from this you can calculate the secret key of the RSA. It was 1996. Also, Paul Kocher in 1996, he just measured the execution time during the execution of the algorithm accurately, and he could also conclude the full key only for measuring the timing of the full execution. Then we had the first SPA, Simple Power Analysis, in 1998, also by Paul Kocher. This is an example of a microcontroller that does an exponentiation. If you do an exponentiation, you want to square and multiply, and here you see a squaring. It consumes less power than a multiplication, and so by measuring the power consumption, only one trace, you can directly see that a 1 or a 0 is processed, and you can also directly read the key that is used for the exponentiation. Yes, and since this time, there were a lot of research papers, side channel attack research papers, for example, in the CHESS, Cryptographic Hardware and Embedded Systems workshop, very famous. And, but so far, there's no documented case that criminals, for example, used power analysts to break a system. And all the researchers, in doing the research, they usually attack their own implementations, so they know exactly what they're attacking, and they can cheat a little bit by generating, for example, a signal that starts the oscilloscope at an appropriate point in time, and that facilitates the attacks. And we now closed this gap by looking at this commercial product, and we knew nothing. When we started the attack, we only had a black box implementation. We knew that the keylog cipher would be somewhere in there, but nothing more. And so now we want to take you through the steps that everyone has, that you would have to undertake in order to power analyze a commercial system. So first of all, you always have to look, what do you want to attack? Analyze the cipher. Yes, there's a question there, please.
Why is it called a side channel?
Do we have a microphone for this guy?
Why is it called a side channel?
The question is called, why is it called a side channel attack? So the answer is because you do not directly, you do not mathematically cryptanalyze the cipher, but you use the side channel of the power to extract the key. It's like someone doing a bank robbery or wants to open a safe in a bank robbery, right? He can use his stethoscope to listen to the sound of the mechanical locks, and then from the side channel of the sound, he can conclude to the right position of the mechanical lock, right? So question is answered, brilliant. So after we know the cipher, we perform some measurements with an oscilloscope, for example, and then we work on these measurements, post-process them, and then we come to the main step, the key recovery.
So let's first look at the analysis of the cipher. So usually if you want to break a device and you know the cipher, you'll just look into the literature and look if someone else already cryptanalyzed the cipher using side channel attacks. In our case, this was not the case. Nobody did looked at keylog before, so we had to do it ourselves. So let's take a look at the cipher. This is what the cipher looks like. It has a 64-bit key, which is stored in this lower register. and it has a 32-bit block length. So that means that the plaintext is put into this state register in 32-bit chunks. Then the encryption runs once, and then in the end you have the cipher text standing here, which you then transmit via the RF interface. And you have the state register is realized as a nonlinear feedback shift register. Nonlinear because we have a nonlinear function here, where 5 taps enter this nonlinear function and are mapped to one output bit. This output bit is XORed with other output bits from the state register and with one key bit, and this is then fed back into the cipher. So this whole thing is clocked 528 times, and then, as I already said, we have the ciphertext which we can transmit via the RF interface. Now what we had to do is we had to come up with a power model, so we can basically predict the power of the device and of the cipher, depending on the key and other things. And for the model we had to make some simplifications. The first simplification is that we ignore the combinational logic part because it's rather small and it consumes rather little power. So we just ignore this middle part, which leaves us with the 2 registers, the key register and the state register. And it's known that the power consumption of registers depends on the number of on the value inside. So generally it depends on the number of toggling zeros and ones in those registers. And we have the key in the lower register, and the key is just being rotated. In each clock cycle, it's just one bit being moved from the left to the right. Actually, the other way around. So basically, the value inside the number of ones or the number of toggles in this register remains constant. So the power consumption of this part is constant. Well, the state register nevertheless changes because of the nonlinear function. The values inside change with each clock cycle, and we can conclude that the variations of the power consumption relate somehow directly to the state register. And now we looked at the feedback function, which you can see here in the equation. So the bit that is fed back at each clock cycle depends on the key, and it depends directly on one key bit. So basically, if we know the state, we can always conclude some information about the key. And this is what we will do later on. So we will analyze the variations of the power consumption to gain information about the key and finally recover the key.
Right, it seems we know everything now about the cipher, so that we can actually proceed with the next step, do the measurements. And for performing the measurements, you can either buy such an oscilloscope as depicted here, a whole digital oscilloscope. It costs you a fortune, it costs you as much as a small car. Or you can just buy one of these USB oscilloscopes, small but also very reliable, also very sufficient. You can connect them to the USB port of your PC, and then you connect this probe to the to the transmitter. You connect it, and then you press on the button several times, and while you press on the button, you measure the power consumption with this thing. All right, it's still blinking. So. For measuring the power consumptions, you have 2 options. Here on the left side, you see some PIC microcontroller here, as used on the receiver side of the garage door, and there is some resistor inserted in series with the device because you want to measure the power consumption, so you need to modify the printed circuit board here and insert this resistor in series with the device and then connect the oscilloscope to measure the voltage that drops over the resistor. So this is rather complicated because you have to modify something in the circuit, and it looks rather ugly, and it's difficult to see here. The second approach is that we just measure the electromagnetic field. That's the emanation of the chip while it operates, only the radiation. And here you can see a so-called near-field probe. It's positioned close to the chip that performs the key lock in hardware, and surprisingly the results from this approach for measuring the field are comparable, almost as effective as the results from this inserting the resistor and measuring the current. And this is the result when we take one of these remote controls and we measure 1 key lock encryption one time pressing this button. This is the result. On the right axis you see the time, on the y-axis you see the current. So you see the device always consumes between 0.5 and 3 milliamperes. And now some trial and error starts, because you need to guess where does the keylog encryption happen. And the beginning is very easy. You press the button somewhere here, and the device starts to operate. And the end is also easy to see, because that's where the device sends the hopping codes. So the keylog encryption must take place somewhere in between these 2 points. And we first guessed it might happen here, then we guessed there. It turns out, no, this is where the device writes into the EEPROM. How did we find out this? We just cut off the power directly at this point in time. We cut off the power of the remote control and started it again, pressed the button again, and the same hopping code was produced again. So we knew the counter is not increased. This must be the writing into the storing the next counter value. And yes, after some trial and error, I think it took more than 1 week, we found that the keylog is actually right here. So from now on, we are only interested in this time period between 20 and 24 milliseconds, and the rest is not important anymore. Okay, we measure this several times, and what we get is a large amount of data, and it's not very well aligned, so it needs some post-processing. This is the area with the keylog encryption. We've just zoomed into it, and the first problem is now we acquire many traces, and we want them to be aligned exactly, because afterwards we want to process them mathematically. So in the case of this remote, we were very lucky, because there's a special feature here in the trace that allows us for starting the oscilloscope very accurately. This was not so easy for the software implementation on the PIC, but there was a question here first.
How good is the internal clock of
the question was how good the internal clock is, and so we will see this now, because it's not so good, because even if you line the traces very, very accurately here at the beginning of the trace, during the encryption, the clock is not so reliable and it's not so stable, and not like some people have got a quartz watch, but it doesn't operate as reliable. And what happens is, if you look at the later point in the traces and zoom in, if you look carefully, there's a blue and a red trace here, and there's always 2 peaks here. You can always see 2 peaks, and they should be on top of each other. That's our wet dream, so that we can analyze it mathematically more easily. And yes, the solution for both compressing the traces, reducing the size of the traces, and at the same time get rid of the so-called clock jitter, when the clock is unreliable, is very easy, called peak extraction. Only take the amplitude of these peaks, and only store the amplitude of these peaks in an array, and forget all the rest. We say all this, not important, no information. We say all the information is only contained in the amplitude of these peaks. Now we have well-aligned data, and we have dramatically reduced the size of this. We come to the most important bit.
Most understandable bit. Yeah, so finally we have all the data gathered, and we want to run the key recovery. We really want to perform the side channel analysis or power analysis attack. And what we now do actually is we take the real power consumption which we just measured, and we correlate it to the hypothesized power consumption which we derived from our power model. And the correlation function looks a little bit scary. It's nothing more than just the correlation function with the power we measured and the hypothesized power. And part of the hypothesized power consumption is the key. So we do this. We produce this model for the different key guesses, and we do not have to guess the whole key at once. So it's a 64-bit key. That's more keys than we can try with a brute force attack on a normal PC. So what we do instead is we take a small portion of the key and guess each portion at a time. So what we did actually in this example is we guessed the power consumption after for round 6 of the cipher. So we had to guess 6 key bits And 6 qubits are 64 possible keys we had to guess. And these 64 key guesses are plotted here. The correlation is between the power consumption which we measured and the